the AE9YL. It really helps to have your Wi-Fi be a ham. You gotta admit that. So what we're going to talk about is first there's a caution. Then we'll talk about space weather data sources along with explanations of the parameters. And then we'll look at which parameters should we be looking at. You know, there's so much stuff out there. It's easy to become overwhelmed, but I think we can break it down into a handful of parameters that will tell you what's going on. And also we'll look at how parameters impact propagation. So the caution is that what we're trying to do is simplify some very complicated atmospheric and ionospheric processes into some simple statements about HF propagation. That can be tough. You can lose a lot by trying to simplify things. Basically, it's okay for a long-term look at propagation, long-term being what's going to happen this month. And that's why our propagation predictions give monthly median maximum usable frequencies and signal strength. Median implying 50% probability, which says our predictions are statistical in nature. We don't yet have daily predictions. Hopefully sometime in the future. I'll talk about this a little bit later in a later slide. Like I said, we have a lot of trouble predicting propagation in the short term. Like is 15 meters going to be good tomorrow as opposed to today? And we just can't do that very well yet. And of course, we generally don't have any knowledge of enhancements and degradations because they happen in such a short term that we just don't understand the ionosphere in the short term as well as we should, but maybe someday. So to illustrate the day-to-day variability of the ionosphere, the data on the left comes from the ionosonde at Wallops Island, Virginia. What an ionosonde does is measures electron densities. And from that, we can determine what the maximum usable frequency would be over that ionosonde for let's say a 3,000 kilometer path. And that's what that data says. So you can see that on August 1st, the MUF is around, well, it looks like about 17.5 megahertz. On the 16th, the MUF was maybe 22 megahertz. So if you look at all the days, you'll see that the lowest MUF was 11 megahertz on the 14th. The highest was on the 16th, 22 megahertz. So why did the ionosphere vary on about 2-to-1 basis over the month of August 2009? Interestingly, the chart on the right kind of shows what August 2009 did. The black is the solar flux. It was pretty much constant, around 66 to 68 or so. The red is sunspot number. You can see August 2009 had no sunspots at all. Every day in August had 0 sunspots. The solar disk was blank. And the magnetic field, which is given by the planetary A index, we'll talk about that a little bit later, in blue, it was pretty quiet. So why did the MUF vary by a factor of 2-to-1 when there were 0 sunspots, a constant 10.7 centimeter solar flux, and the Earth's magnetic field was relatively quiet? Well, the bottom reason, the baseline, the reason is that solar radiation and geomagnetic field activity aren't the only two parameters that determine what the ionization is going to be. The other one is we're beginning to learn a lot more about right now is events in the lower atmosphere coupling up to the ionosphere. So we've still got a lot to learn, and once we eventually figure out that third parameter, that's when maybe we'll have some day-to-day or daily predictions. Enhancements and degradations, I mentioned those earlier. I have several short-term events that I just can't explain. It's because we just don't understand the short-term variation in the ionosphere. Most of those events are enhancements. You know, there was an unusual band opening. You know, why did 12 meters open up? Or why was the signal strength significantly higher than predicted? What's going on? Some are degradations. A recent example was K7SS out on the West Coast working JD1 BMH, Ogasawara on 20 meters via a long path. But the short path is predicted to be a heck of a lot better than long path. So why did that happen? And just don't have any answers. And one of the problems is there's just not enough data to see what's going on. You know, ionosphere data and total electron content data from GPS, that's mainly over land. So we have a kind of a decent understanding of what the ionosphere does over land, but over water, you know, the oceans are what, 70 to 75% of Earth. So we just don't have enough data. And one of the other things for the low bands, we don't have any ionospheric absorption data, or at least nothing on a real-time basis. So our understanding of 160 meters can be kind of low. Okay, now let's look at some space weather sources and explanation with the parameters. Here's some websites you can go to. You can find all kinds of space weather stuff. What we're mostly going to focus on is the N0NBH banner that appears at, for example, the QRZ.com and elsewhere. There's the URL for the N0NBH banner. Next one down is Dr. Tony Phillips. He does the spaceweather.com website. The Space Weather Prediction Center, SWPC, that's part of NOAA, and they have all kinds of data there. VE3EN, he maintains the Solarham.net website, lots of solar data. And then hopefully you've watched some of the videos by Dr. Tamitha Skov, Whiskey X-Ray 6, Sierra Whiskey, Space Weather Woman. And she has her website there with videos. And she talks about what the sun's doing and how that impacts propagation. There are a lot of other websites out there of a general nature, and many others that drill down into one specific parameter. And you know, the internet you can learn a lot, assuming you believe all of it. But, you know, you usually can on this kind of stuff. So here's the banner that N0NBH puts together, and a lot of people have picked this up. I just pulled this morning from QRZ.com, so that's why the date is 10 April, and that was at 11:38 UTC. So that would be 7:38 in the morning here for us. Fort Wayne is on Eastern time. We're pretty far west in the Eastern time zone, but you know, we're still on Eastern time. SFI is the latest 10.7 centimeter solar flux index. SN is the sunspot number. Okay, A is yesterday's A index. It tells us the activity of the Earth's magnetic field, and it's an average of the 8 3-hour K indices. And that brings us to the K index, which you do first, and then you can translate that into the A index. The K index is a 3-hour index. So there's 8 of them during the day. Tells of the activity of the magnetic field. The PLN-TRY after A and K means it's not just from one station, it's a planetary index. In other words, they average a bunch of observatories. X-ray is the background radiation at very short wavelengths, 0.1 to 0.8 nanometers. And of course, X-ray radiation is associated with solar flares. And solar flares are classified as A, the smallest, up to B, up to C, up to M, and then up to X, which is the largest. It's a logarithmic scale too. So things can be kind of big. We've had solar flares exceed the upper limit on the X values. We haven't named anything above that, but it happens every once in a while. So maybe one of these days we'll have something ABCMX and something else, who knows. 304A, that's 304 angstroms. That's the extreme ultraviolet radiation at 30.4 nanometers. Extreme ultraviolet radiation is the true ionizing radiation for the F2 region. So just remember that sunspots and 10.7 centimeter solar flux are just proxies for EUV, which is really what's important. Of course, we measure EUV with satellites that are in Earth orbit or stationary somewhere up there. And the little note there below the EUV is 26 to 34 nanometers is responsible for about 60% of the F2 region. So looking at that 304A value probably tells you quite a bit about the F2 region. There's a lot more stuff. The PTN flux, that's the proton density in the solar wind. There's different measurements made depending on the energy of the protons. ELC FLX is the electron density in the solar wind. Again, it depends on the energy level of the electrons that you're measuring. Aurora is a scaled power from 1 to 10, and it loosely correlates to the K-index. The K-index goes from 0 to 9, so you can see where that might have a correlation. AUR lat is the lowest latitude impacted by aurora. Of course, the lower the latitude, the more active the Earth's magnetic field is. And perhaps you'll see auroras down in Georgia. BZ is the orientation of the interplanetary magnetic field. BZ is, the Z component is perpendicular to the ecliptic, which is the plane that the Sun and Earth are in their orbits. And it's pretty much a north-south orientation of the interplanetary magnetic field. Now later on, we'll get to, what are some values and what do we want. Solar wind is just the speed in kilometers per second. Quiet time is about 400 kilometers per second. SIG noise level, that's the noise level in S units due to magnetic field activity. MUF US Boulder, that's the maximum usable frequency in megahertz at the Boulder ionosonde. As you can see for, whoops, went to the wrong, okay, as you can see, MUF US Boulder at 7:30 this morning was 11.64 megahertz. So that says, okay, 30 meters is probably open, 20 meters not yet. It's just too early in the morning. And solar flare probability is self-explanatory. What's the chance of having a solar flare today? Okay. Spaceweather.com. There's a lot of data there, and I'm not going to go over all of it because a lot of it is the same as you saw on the N0 NVH banner. When you go to spaceweather.com, in the left column, you'll see solar wind, X-ray solar flares, sunspot number, spotless days. It's good to know sometimes, especially at solar minimum, and the 10.7 centimeter solar flux. The middle column is a lot of good discussion on a variety of subjects, and that's what Dr. Tony Phillips talks about. He talks about coronal mass ejections, CMEs. He talks about aurora, near-Earth asteroids, cosmic rays, and many links to specific data. So that's a good general website where you can learn a lot, especially the middle column with text and explanations. NOAA has the Space Weather Prediction Center. Right at the top of the homepage, you'll see RSG. On the left is the 24-hour observed maximums. In the middle is the latest observed, and on the right is predicted for a given date. Disturbances to propagation are categorized as G, S, and R. G is for a geomagnetic storm, generally caused by Earth-directed coronal mass ejection or a coronal hole. S is a solar radiation storm. That's due to energetic protons that are released by a really big flare, an M or X class flare. R is radio blackout, which is due to the very short X-ray radiation that's released from a big solar flare. The scale for RSG is 1 to 5, minor to extreme. And there's the URL that explains all that stuff in more detail. Here's just a big picture of disturbances to propagation. And it's divided into the G, S, and R categories. You can see there's the North Geomagnetic Pole. You can see the auroral oval is centered on that. And of course, in the midnight sector, you can see where the terminator is going in the lower kind of half of the Earth. There was some auroral activity that night. I don't remember what night it is, but whatever. But it kind of gives a picture of what can happen and what can disturb our propagation. In essence, a geomagnetic storm, we could have decreased F2 region MUFs at the high latitudes. That'll screw up propagation. S, solar radiation storm, could have increased D region absorption in the polar cap area. That's the area within the auroral oval, and that would affect paths like from Georgia into deep Russia or India over the pole paths. And the radio blackout is increased D region absorption on the daylight side of the Earth. So there's a very brief picture of disturbances to propagation. The Space Weather Prediction Center also has 6 panels on the home page. Top left is the sun in extreme ultraviolet wavelengths at 19.5 nanometers. Again, it's not, the 304A, 30.4 nanometers that's on the N0 NVH banner. It's close, but it's not that. The middle top is coronal mass ejections. You can see the occulting disk blocking the sun, so we can see what goes on, outside the sun. The top right is aurora forecast. What's the chance of aurora? Green kind of says, well, not too bad. Don't worry too much. If it gets into, yellow, orangish, and red, and then we could see some degradation of propagation via the F2 region. Bottom left is the GOES X-ray flux, and that's where the X-ray on the N0 NVH banner comes from. You can see on that day things were pretty quiet, and the solar flares, looks like there were kind of 2 solar flares, and they were A level, the lowest level. And that's kind of reasonable since we're at solar minimum right now. In the middle is the GOES satellite proton flux. That's up at geosynchronous altitudes. It's not the N0 NVH proton density, different measurement. And there's in the bottom right is the estimated planetary K indices. And that's where the K on the N0 NVH banner comes from. And you can see there that mostly things were kind of calm. Green is less than 3. Yellow is a K index of 4. Things are starting to get maybe a little bit bad. And if K index of 5 up to 9, well, that'd be in red and might signify we may have trouble on the HF bands. Solarham.net by E3EN. There's a lot of data, a lot of similar data. All I can say is, phew, and that guy there sweating. A lot of data, and it's very similar. He just presents it in a different way. That's all he does. He also has some great 6-meter data, sporadic E data. So there's a good website to just go take a look at. Okay, so which parameters should we look at? Well, like I said earlier, I think there's just way too much information out there, but it's very colorful. It's really nice to look at. But here's what I think is important. The solar flux index and the sunspot number. That's because they indirectly tell us how much ionizing radiation there is for the F2 region of the ionosphere. Related parameters that we went over are 304A, MUF, US Boulder, and X-ray, the radiation from a big solar flare. Also, the K and A indices tell us how active the Earth's magnetic field is. Related parameters that we went over are the B sub Z, the solar wind, the GSR categories, and particles from big solar flares. So I think we can break all that stuff down into those parameters, and let's take a look at how they impact propagation. First, we'll look at the solar indices, basically. I think what they're, just what is the sun doing radiation-wise. So SFI and SN, again, are proxies for the true ionizing radiation, which is extreme ultraviolet for the F2 region. A good point to remember that at solar min, even though the SFI, solar flux index, has bottomed out at around 65, and there aren't any sunspots, there's still enough extreme ultraviolet radiation from the sun to keep 20 meters open during the day and early evening. And of course, that also means that there's enough ionization for frequencies lower than 14 megahertz. So what the SFI and SN give us is an indication of openings on the higher bands being 15 meters, 12 meters, and 10 meters. Now, the daily SFI ranges from 65 to 350. 65 is solar min. A big solar cycle would be 350. The daily sunspot number can go from 0 to 450. That's solar maximum. And the daily extreme ultraviolet, that 304A, it's going to go from about 70 at solar minimum to somewhere around 500 at solar maximum. So that gives you the bounds of those three parameters. And here's a little table that kind of gives you an indication of what we need for 15, 10, and 6 meters to be open. For example, the 10.7 centimeters solar flux should be at least 90 for many weeks. And that'll give us consistent day after day propagation on 15 meters. Translating that to a sunspot number, it says we should have a sunspot count of 50 for many weeks. And that will give us day after day propagation on 15. And there's the EUV value for keeping 15 meters open. 10 meters, of course, we need more solar flux, we need more sunspots, we need more EUV. And 6 meters, we need even more SFI, even more sunspots, and even more EUV values. Now, what you can do, of course, is just look at that MUF US Boulder parameter. That's real time, and it gives a direct indication of F2 region propagation. Probably, at least within the United States, although it's just over Boulder, but it's probably a good estimate for the continental US. Okay, K, A, B, Z, solar wind, GSR, and X-rays. Again, K goes from 0 to 9, it's a logarithmic scale. A goes from 0 to 400, it's a linear scale. So Remember I said that the A index is the average of the 8 K indices? Well, the K index is logarithmic. You can't average logarithmic values. So you have to convert K to a little a, which is a linear equivalent of the logarithmic K index. And once you've got the linear equivalent, then you can average and get the big A index, which is again the average of the 8 3-hour K indices. And there's a translation between the linear equivalent A index and the logarithmic K index. The BZ component of the interplanetary magnetic field goes from about -100 to about +50. The solar wind goes from 400 or less, and it can go as high as 2,000 kilometers per second when there's a really big coronal mass ejection occurring on the sun, or a coronal wind with a high speed solar wind. So it kind of tells us that we may be in for trouble if the solar wind is way up in thousands of kilometers per second. Again, GSR goes from 1 to 5, minor to extreme. X-rays go from A 1.0, which is the smallest, up to X 9.9, the biggest, or even higher, as I mentioned before. In general, what we want is a K less than or equal to 3, which translates to an A less than or equal to 15. We want BZ to be positive, or a little bit negative is okay. And what that means is the interplanetary magnetic field is not coupling into the Earth's magnetic field and causing problems. We want the solar wind to be not too much greater than 400. 400 is a quiet time. We want GSR values basically at 1, maybe 2, but not much higher than that. And we'd like the X-ray parameter to be at A, B, or C, because M and X X-rays can cause solar radiation storms and radio blackouts. Now, we've gone through a lot of data, but do we really need all that data? Well, that's because the internet is putting on more and more real-time data that helps us get a picture of what's going on. For example, here's a map of maximum usable frequencies. It's done by KC2G. He uses real-time ionosphere data, and that's what those values are in the circles. Then he adds contour lines to try and give you a pattern of what the worldwide MUFs are. The map you can see also shows gray line. And what I've highlighted is a path from the Southeast United States to DL. And at the time that that picture was taken, you can see that 20 meters is likely available because all the numbers in the contour lines are above 14 megahertz. Also says maybe 17 might be open. This data is updated every 15 minutes, so you can get a pretty good worldwide picture of what the ionosphere is doing in real time. Well, within a couple of minutes. Now, here's another example of real-time data is dxmaps.com. So what it does is plots QSOs that have happened. There are other equivalent maps, PSK Reporter, WhisperNet, the reverse beacon network you can use to figure out where your signal's going. And of course, there's the IARU, Northern Cal DX Foundation beacons. And in a 3-minute period, you can tell what the worldwide propagation is doing on a single band, 20, 17, 15, 12, or 10. Now for the DX maps, you can select a world view. You can select a North American view or whatever, and you can select the band. And what I've shown here is 17 meters for the world. And you can see 17 meters was open from generally the East Coast over to Europe and something into South America, even South Africa, and then down to 3B9CW down there in the lower right-hand corner. So that's a great way to see what a band is doing right now. So why do you need to You know, go look at all that A and K and the solar flux and SN numbers, right? Now here's a long-term look at several of those parameters. This comes from Solinfo/solar. It's a year's worth of data. It gives the AP index, the A index, the planetary A index, the daily sunspot number, the 30-day sunspot number average, the daily solar flux index, and the 90-day solar flux index average. You can see the legends up in the top left corner. The 10.7 centimeter solar flux is black. You can see since we're at solar minimum, it's kind of flat, down around 70, a little bit lower. You can see there was a nice spike at the end of 2020, and it gave us some great worldwide propagation on the higher bands, 15, 12, and 10. But things have settled down now back to about solar minimum again. You can also see this 27-day solar rotation period in this data, and it'll be more obvious when we do get some more sunspots and more solar flux. It's kind of tough to see it when the solar flux is constant at solar minimum. Okay, I should mention that we have two sunspot numbers. Of course, the original data set was created by Rudolf Wolf in 1849, and he defined how we should count sunspots. Now, when his successor took over, Alfred Wolfer, he counted more sunspots than Rudolf did. So he applied a fudge factor of 0.6 to his data to make his accounts agree with his predecessor. Now, this has been carried through to the present. And there was concern about these old sunspot numbers. And that concern began in the 1990s. There were 4 sunspot workshops held beginning in 2011. The result was a new sunspot data set, which has been labeled version 2. It removed that 0.6 factor, and it corrected some other less major issues. The Royal Observatory of Belgium began reporting the new sunspot numbers on July 1st, 2015. So you gotta kind of beware of what sunspot record people are using. Some of the early cycle 25 predictions were in terms of the old sunspot record, V1, and some were in terms of the new sunspot record, V2. And here's a comparison of the old record versus the new record. The blue is the old data, red is the new data. You can see what the difference is. We now believe that there were more sunspots than originally thought. What this also tells us is our model of the F2 region of the ionosphere that's used in our propagation predictions. Well, that was good for the old data that it was correlated to, but now we got new data. So if you put in new data into an old propagation prediction program, well, it's going to result in your prediction being optimistic by about 1 band. Of course, that's mostly at solar maximum. You can see the 2 records are pretty close at solar minimum. I mean, you know, 0 is 0. Doesn't matter which one you're reporting. So, summary, there's lots of data available. I don't believe our amateur radio operations need all of it. I think you should focus on the basics per slides 20 and 21, and also keep an eye on that real-time data on 22 and 23. That'll give you a picture right now, and of course it takes into account all that stuff to give you, what the ionosphere is really doing right now. And a great way to learn more is just get on the air and operate a lot. Experience is a great way to gain knowledge. One thing you can do is enter contests, go after your worked all states, go after EXCC, go after worked all zones. But mostly, just go out there and have some fun. And I think HF offers all kinds of fun. There's just a variety of subjects or topics you can go work with. You can do MCOM, the hurricane nets and all that. You don't have that on VHF. Well, you know, except if you live in Puerto Rico, and VHF would be good, pretty good for that. But up here in the States, we need HF to really make some MCOM activities. So that's all I had, Keith and Greg. If there are any questions, I'm glad to try and answer them.
All right. Well, thank you very much, Carl. That was very interesting. I'd invite anybody that has a question to unmute yourself and ask away.
There's some references too there that I had on the last page. The propagation chapters of the ARRL handbook and antenna book are very good. There was a
Carl,
book.
I've got a question.
Sure.
On slide 26, you've got the version 1 and 2 propagation chart. What's the prediction for the next cycle coming up? I noticed it was going down, down, down.
Yeah, well, I'm aware of 56 predictions for solar cycle 25. Why are there so many? That's because we just don't fully understand what generates a solar cycle. You know, we know it has to do with the plasma flow within the sun and the magnetic field flow within the sun, but we just don't have it all figured out yet. Now, 89% of those 56 predictions, in other words, 50 of the predictions are for a smaller than average solar cycle. And what that means is mostly it's probably going to look like cycle 24, which was quite low, lowest in our lifetimes, not the lowest in our recorded history though. There are 3 predictions for an average cycle, which would be just a little bit bigger than cycle 23 was, which it was a decent cycle. We had good F2 propagation on 6 meters at solar maximum. So that's not bad. Then there are 3 other predictions that predict a very big solar cycle. All we can do is wait and see what happens. Again, we just don't understand enough, and that's why we have so many predictions. Once we fully understand what goes on inside the sun, there won't be as many predictions, and hopefully they'll be very accurate. But we're not there yet, that's for sure. So 25, the consensus of solar scientists is that it's going to be another small one.
Okay, thank you.
Okay. Not good for the higher bands, but around solar maximum, we'll still have good worldwide propagation. But not like cycle 19 or 21 or 22, which were really great. You know, how many hams are there that have been licensed just within the past several years?
A bunch in our group.
Yeah, and one of the questions that you guys probably ask, so what's so great about 15, 12, and 10 meters? For the past couple of years, there's basically been nothing going on. Yeah, that's right. But just wait a couple more years when cycle 25 gets around its peak, and then those bands will be very active with worldwide propagation. So think about getting ready for that with antennas and all that kind of stuff. Okay, I'm done with that.
Carl, this doesn't have anything to do with propagation, but does the solar cycle have anything to do with global temperatures?
Oh, there's some people who think they do. I don't think our models of climate adequately take in the sun. It's a very complicated thing, but I think solar cycles do impact our climate. You know, maybe it's not the whole, the whole thing, but I think there's some impact to that. I think, our activities here on Earth combined with what the sun's doing may explain a lot. And we haven't looked at the sun enough, I don't think.
Interesting.
Yeah, it is.
I really enjoy spaceweather.com. That's actually my start page. When I start Chrome. And I actually communicated with Dr. Phillips a few years ago and suggested that he add the solar flux index to that page, and he did. And
Yep.
I was happy to see that.
Yep, that's good. Yeah, he's that left column has a lot of good data in it. It tells you a lot.
All right. Does anybody else have questions for Carl? If not, I'll go ahead and end the recording.